Hello learners, welcome to this course on Embedded System Design using AT89C51 microcontroller. In this tutorial, I will be discussing about how to design a real-time clock using your microcontroller. So the real-time clock which we are going to use is DS1307 IC, which has 64 by 8 memory locations. And it's a serial real-time clock which gives date and time information through a serial interface known as I2C. So the complete code and simulation of this project is available in this GitHub repository link which is given below. So now let us start with the design of your real-time clock. So in order to understand the real-time clock, first we have to understand the DS1307 IC. So it counts seconds, minutes, hours, day of a month, day of a week, and a year. So all this information will be counted and stored in the real-time clock DS1307 IC. So it is a 8-pin IC. So here I show a pin details of this DS1307 IC, where X1, X2 is where we have to connect a oscillator. So this oscillator will be of 32.768 kilohertz we need to connect, and this IC requires a battery source. So a battery voltage of about 3 volt needs to be provided so that even the power goes off to the microcontroller, the information stored in this IC will be retained. So thereby there will not be any loss of information even though the power is not applied to a microcontroller. And the pin number 4 is your ground. Pin number 5 and 6 is nothing but the I2C interface, integrated circuit interface. So it's a serial communication interface through which the information in the IC will be transferred to the microcontroller. And this IC also has a feature to generate a square wave output. So four different frequencies can be generated, and it can be used for other devices too. And the pin number 8 will be your VCC. This clock, it operates in both 12-hour format and 24-hour formats. In case of 12-hour format, we can have AM and PM indicators too. And the information which is stored in this IC, it will be in terms of BCD format, binary coded decimal format. And as I said, this IC will communicate with the microcontroller with the help of a I2C interface. So it's a 2-wire serial interface where I have 2 lines. SCL stands for serial clock, SDA stands for serial data. So in addition to this date and time information, we can also have 56 bytes of non-volatile RAM memory. It can be used for data storage. Altogether it is 64. So 56 bytes for non-volatile RAM plus 8 bytes for your time and date information, which we can store it in this IC. And as I said, we have programmable square wave output. So 4 different types of frequencies can be generated, like 1 Hertz, 4 kilohertz, 8 kilohertz, and 32 kilohertz. So here I show a typical block diagram of this IC. So where we have this 64 bytes here. Out of the 64 bytes, initial 8 bytes is for real-time clock, and remaining 56 bytes we can use it for a storage. So the data can be communicated through this serial bus interface, which is your I2C. So I2C makes use of 2 lines, serial clock and serial data. So the address can be sent through this I2C bus, and depending upon the address and the write or read information, the information can be obtained from this RTC chip. So there is a power control module where we try to give the supply for IC and ground, and we also need to interface a V battery, so that the time and date information keeps updated even though the power supply is cut off for your microcontroller. And there is a square wave out module where we can generate 1 Hertz or 4 kilohertz, 8 kilohertz or 32 kilohertz. So in order to generate this square wave, we make use of the oscillator circuit. So usually the oscillator frequency which we will be using is 32.768 kilohertz. So when we see the RAM location, RAM address map, so the first location at 00, we will be having the second details, and in 01 we will be having minutes, 02 we will be having hour information, in 03 we will be having the day in the sense in a week which day it is, whether it is a first day, second day, third day, so those information will be there. In 04 we will be having the date information, 05 will be having the month information, 06 we will be having the year information, and 07 is for control data. So this control information is for square wave generation. And remaining space from 08 to 3F, we have 56 bytes which can be used for your data storage. Now let us look in detail about what are the internal components of this RAM memory. So here I show this RAM memory. So at 00, as I said, we have second information. So second in the sense it will vary from 00 to 59. So this information will be stored in terms of a BCD format. BCD format in the sense if it is 59, so we will take the BCD value of 5 and BCD value of 9. So BCD value of 9 will go here in this 4 bits, and BCD value of 5 will come here. And the 8th bit, which is your clock halt bit. So if this clock halt bit is 1, then the clock will be disabled. If the clock halt bit is 0, clock will be enabled. So this will be used while utilizing our square wave generation. Same way in the second location in 01, we will be having minutes information. Again, minutes can be from 00 to 59. So again, this 9 BCD format will go to the lower 4 bits, and 5 BCD format will come to the upper 4 bits, and the 7th bit is not used here. Same way in 02 we will have the hour information. So in hour information we can have a 12-hour format as well as a 24-hour format. In case of a 12-hour format, the lower BCD will be given here, and the upper BCD will be available in this bit, because 1 bit is required, because either it will be 0 or 1. So in order to select a 12-hour format, here I have to specify an appropriate value to select the 12-hour format. If it is a 24-hour format, in that case my value will vary from 00 to 23. So here, in order to get the lower value, so for example I have 18, right? So 18, this 8 will come here, and the upper one will go to this 2 bits, because here I have two things, either it can be 08 or 18, or I can also have 23. So maximum value is 23. So this upper BCD can vary 0, 1 and 2. So 0, 1 and 2 means minimum I require 2 bits. 0 will be represented by 00, 1 will be represented by 01, 2 means it will be represented by 10. So I require 2 bits to store this upper value. So for that we make use of this 2 bits. In case of a 12-hour format, we also use this bit for AM or PM indication. Next one is your 03. So in 03 location we have a day information. So day information in the sense in a week what day it is, whether it is the first day, second day, third day. So we have 7 days. So my value can vary from 1 to 7. So this number requires 3 bits, right, from 000 to 111, right. So this represents 0 and this represents 7. So in order to store this information we use 3 bits here. Same way in 04 location we have the date information. So date, again it can be 1 to 28 or 29, or 1 to 30 or 1 to 31. So for that the lower number is represented in this lower 4 bits, and the upper number will be represented by this 2 bits. So here you can see the upper, it can be either, it can be 28 or 29, it can be 30 or 31. So in this case, if you see the upper, so in order to represent 2, 3, right? So I require minimum 2 bits. So 0, 0 means 0, 0, 1 means 1, 1, 0 means 2, and 1, 1 means 3. So minimum I require 2 bits to represent this 4 numbers. So that is why we use 2 bits here. Then in case of your month, it is stored in location 05. So in 05, again our month will vary from 01 to 12. In this case, my upper bit can be only either 0 or 1. So 1 bit we try to use it here. In case of a year, it is stored in 06 location. So in 06 location, our year can be varying from 00 to 99. So here the lower 9 is stored in the lower 4 bits, and upper 9 information will be stored in the upper 4 bits. So from 2000 to 2099, we can keep track of our data. Then the 7 is your control, which is mainly used for square wave generation. So here for this, if you see this, out is your output control. So which will be like a enable line to send your square wave out of your IC. And this is square wave enable, and RS1 and RS0 will be used for selecting the frequency of output. If RS1, RS0 is 00, in that case 1 Hz will be coming as an output. If it is 01, 4 kilohertz will be coming as an output, 10, 8 kilohertz will be coming as an output, and 11, 32 kilohertz will be coming as an output. So that is how the data is stored in your DS1307 IC in the RTC part. So in the RTC part, only 8 bytes are used. So remaining 56 bytes are used as a general purpose RAM. Now let us talk about the communication point of view. I have this information in the RAM memory. So this information should be sent to your microcontroller upon request. So for that, what we are going to do, we are going to make use of a protocol called as I2C protocol. I2C stands for Inter-Integrated Circuit Protocol, which makes use of 2 lines, SCL and SDA, serial clock and serial data. And it's a synchronous based communication. Synchronous based communication in the sense our data will vary with respect to the clock signal. So the speed of communication is determined by the clock speed. So here the data will be sent in terms of a packet format. So each packet will have a start condition. So start condition means what? When I have a SCL to be high, at that time if I have a SDA to have a transition from high to low, then that indicates your start condition. Our SCL should be high, and during that clock period, my SDA data line should go from high to low, which indicates a start condition. Then comes a 8-bit address or data. Out of this 8 bits, the 7 bits will be used as a address for a slave. Right? For RTC DS1307, the address is already fixed. It is available in the data sheet, and this is the address 1101.000. So 7-bit slave address. So 7-bit slave address in the sense we can connect up to 2 power 7 devices. So 2 power 7 is 128, right? So up to 128 devices we can connect with our microcontroller in a bus format. So here in this first, after your start condition, we will send the address of the slave. So while sending the address of the slave, the MSB bit will come first and the LSB bit will come at the last. So after putting the 7-bit address, the 8th bit will be indicating whether it is a read or write operation. Whether master is requesting data from the slave or it is going to write the data into the slave. If this bit is 1, it is your read operation, right? This is R W bar. If this is 1, then it is read operation. If this bit is 0, it is write operation. So after sending the address of the slave, so depending upon this read or write, if it is read, what will happen? The slave will put the data into this bus. If it is a write operation, the master, our microcontroller, will put the data into this bus. After each byte, there will be an acknowledgement signal. So that acknowledgement signal will be given by the receiver, right? So after sending this 8-bit data, out of this 8-bit data, we have 7-bit address and 1 bit for read-write option. The 9th position, I have a clock signal. At that clock signal, the receiver will make the line, SDA line, to be low. This indicates the acknowledgement information. If this 8-bit data is properly received, during the 9th clock pulse, what will happen? The receiver will try to make the SDA to be low. Then the transmitter will understand, okay, the data has been received by the slave, or the data has been put by the slave into the bus. Then comes again your data. Once address is sent, we can keep on sending the data, right? So as well as the slave also keep on putting the data into the bus. Once all the data is over, right, then finally we have to send the stop condition. So for the stop condition to occur, we will be having the clock to be high, and there will be a transition from 0 to 1 in case of your SDA. So SDA will change from 0 to 1. It indicates the stop condition. So in a start condition, what happens? My SCL is 1 and SDA changes from high to low pulse. For stop condition, SCL is 1. Now the SDA changes from 0 to 1. It indicates the stop condition. And before the stop condition comes, when the last byte is transferred, now the acknowledgement for the last byte will be not of earlier acknowledgement. So earlier acknowledgement is low signal, right? For the last byte alone, the acknowledgement will be 1, which is the not value of earlier acknowledgements. So when this is received, then automatically the device will understand, okay, this is the last byte which it is going to receive, and then it will sense for the stop bit. Now let us look at this in detail in both write operation and read operation. So first one is your data write. Data write, slave receiver mode. Now the microcontroller is going to put the data and the slave is going to receive it. Okay, so first what it does, the microcontroller, it puts the start bit. So start bit, already I have said, SCL should be high and SDA should be going from high to low pulse. Then it gives the 7-bit address. So for DS1307 IC, the address is fixed. Okay, so the address is 11010000. And then we put the read-write operation. Right? Since we are going to write the data, we will put the 8th bit as 0. Then it will wait for the acknowledgement from the receiver. Right? So the receiver will make the SDA line to go to low. Then we send the word address. So word address is a 8-bit address. Here you can see this is a word address 00, 01, 02. So this is a word address. So this address we have to send. This is a 8-bit address. After sending this address, again the master will wait for the acknowledgement. Then subsequently the data will be sent. So first send, if this is the address, for example here the word address is 00. In that case what will happen? The first data, second, will come here. Then again acknowledgement signal. Then minutes information will come here. Acknowledgement. So like that it goes on. Next hour information, then acknowledgement. So when we are going to send only this 3 bytes, second, minute and hour, right? So the first two, for second and minute, the acknowledgement will be 0 and 0. When the last byte is sent, our information is sent, the acknowledgement will be 1 because it will be a complement. Then finally we will be having a stop bit. So stop bit is nothing but your SCL will be high and SDA will change from 0 to 1. So this is how the data is written into the slave. Now let us look at how the master is going to read the data from the slave. That is data read mode and slave transmitter mode. So again the master will send the start signal, give the slave address, then it will set the read bit. Okay, read bit is 1. Then it waits for an acknowledgement. Then once it has sent, then now the data will be sent by the slave. So the data will put the first byte, then an acknowledgement, second byte, acknowledgement. So like that it goes on. When it receives, when it puts the last byte into the bus, we will be having a not acknowledgement, right? So here the acknowledgement will be 0, 0, 0, and for the final data it will be 1, and then we will be having a stop bit. So that is how the data is read from a slave. So now let us come to the application where we will be using AT89C51 microcontroller. So this will be interfaced with your DS1307 IC. So the important thing to note here is our AT89C51, it does not have a internal hardware I2C module. It has only UART module, right? So there is no hardware I2C module into our IC. So what we are going to do, we are going to generate this I2C module in a software way. So we are going to create a software based I2C module. There is no hardware module available, so we are going to use a software module. So in order to do that, we select some 2 lines in our microcontroller. So we are going to pick port 2.0 and 2.1, and we are going to treat it as SDA and SCL lines. So 2.0 will act like a SDA and 2.1 will act like SCL. And this can be done for any pins in our microcontroller because it's a software UART. Okay, only by writing a code we are going to generate this communication protocol. So we can select any 2 pins and we can make them as a SDA and SCL. And in order for this I2C module to work, this SDA and SCL by default it should be at logic high. So to have that, we use a pull-up resistor where we connect a 4.7 kilo ohm and it is connected to a supply. So thereby these 2 lines will be at logic high. And this IC is connected with a crystal of 32.768 kilohertz. Then we connect a 16x2 LCD where I use port 3 of our microcontroller. So port 3.0 is connected to RS, port 3.1 is connected to enable, and port 3.4 to 3.7 is connected to D4 to D7 of your LCD. So we read the data from this IC and send the data to your LCD for displaying your time information. So this is a typical circuit where I have a AT89C51 microcontroller, and here I have oscillator circuit where I connect a oscillator frequency of 11.0592 megahertz. So this frequency is particularly selected for having a particular baud rate. Then I have a reset circuit here. Then we connect a DS1307 IC where I connect a 32.768 kilohertz, and the 2 lines port 2.0 and 2.1 I am going to use it as SCL and SDA. Then these lines are connected with a pull-up resistor so that by default these lines will be at logic high. Then we also connect a battery here, 3 volt battery, so that even the power supply goes off for the microcontroller, still this IC will keep on working. And port 3 we are going to use it for connecting to your LCD. So after doing the program, you can see that the output is displayed here. The time information, hour, minute and second information can be displayed in your LCD. We will see how we are going to do this. So the complete circuit is built using a simulator called as Proteus 8 Professional, and the C programming is done using Micro C Pro for AT51 IDE software. Now let us look at the program. So first we try to do the LCD initialization, where LCD RS is connected to 3.0, enable line is connected to 3.1, RW bar line of your LCD will be grounded. And LCD's D4 will be connected to 3.4, D5 will be connected to 3.5, D6 will be connected to 3.6, and D7 will be connected to 3.7. So this indicates the LCD module connections. Then we take two lines, port 2.0 and 2.1. So 2.0 I am going to use it as a SDA, serial data in I2C. Same way, port 2.1 I am going to use it as SCL, serial clock, as I2C module. Then we use a delay function where we try to generate a microsecond order delay. US indicates it's a microsecond order delay. So 5 microsecond order delay function we try to write. So now we will try to define the start condition. So in start condition, what we have to do? My SCL should be high, and SDA, what should happen? So SDA, we should have a high to low pulse, right? So that is what we define it. First we make SDA to be 1, SCL to be 1. So that first initially my SCL is high, SDA is also high. Then after 5 microsecond delay, what we do? We make SDA to be 0. So it goes from high to low pulse. Till the time the SCL remains high. So this indicates the start condition. Then after this SDA transition, we make this SCL to go to low. So this indicates the I2C start condition. Then we write a code for stop condition, where what we do? SDA, we are going to have low signal. SCL, we are going to have a high signal. And then after 5 microsecond delay, what I am going to do? SDA, we are going to change it to high. Okay, so low to high transition we are going to make. Okay, during the time SCL will be 1. SCL will be 1. So low to high transition indicates it's a stop condition. Next, we are going to write using I2C. To write a data through I2C, I am going to get the data. Then what we do here? We are going to send the data one by one. So we run a for loop for 8 times. I equal to 0 to I equal to 7. Okay, so we are going to run this for loop for 8 times from 0, 1, 2, 3, 4, 5, 6, 7. 8 times we are going to run. What we are going to do? We are going to take the bit one by one and we are going to send it out. So first the data is initialized to some value, right? For example, I have the first bit, right? So 0, 0, 0, 0. 0, 0, 0, and the first bit will be 1, right? In that case, what we are going to do? We are going to, this is your data, right? So let us assume this is the data, right? So I am going to send this data out first. So in order to do that, what I do? I take 8, 0. So 8, 0. So this is 0x80, right? So data and 0x80 I have to do. So when I add this, what happens? This will be 1, other bits will be 0. So this is a valid condition, right? So valid condition. So this condition is true. In that case, I am going to send 1. If this condition is not valid, then we will be sending 0, right? Since this is a valid number, right, we will be sending 1 to your SDA. So SDA will be sent with 1. Then we make the SCL to be 1. Wait for 5 microsecond delay, then SCL goes to 0. Then what we do? We shift the data. When I shift the data, what happens? This one will go out. The next data will come to this position. Again I do AND operation with this 0x80. So now this will be 0. In that case, my output will be 0. So 0 means this condition is false. So we will send 0 as an output to your SDA. Then again I do this SCL high and low operation. So like this one by one. So first this bit is sent, next to this bit, next to this bit, this bit. So like that we keep on sending the data until all the 8 bits are being transferred. After transferring all the 8 bits, okay, after transferring all the 8 bits, we need to wait for the acknowledgement, right? So SDA is set with 1 and SCL is set with 1, right? At this time, the receiver, okay, this is from transmitter point of view. So transmitter will make the SDA to be 1 and SCL to be 1, and the receiver, once it receives the data, it will change this SDA from 1 to 0, right? So this will be done by the receiver side. That indicates it's an acknowledgement. So we are waiting for an acknowledgement. Once the acknowledgement is received, that packet is complete. So that is how we write the data through your I2C module. Now let us see how to read the data using a I2C module. So for reading the data, we use this function character I2C read. We get the acknowledgement signal as an input. So the data variable is initialized with 0. So for reading it, first we will make SDA line to be 1. Then we are going to read the data for 8 times. Again, I is going to be varying from 0 to 7, which means 8 times I am going to read the data. First bit, second bit, third bit, fourth bit. So like that, 8 bits I am going to receive. How we are going to do that? We will make the SCL to be 1, right? Wait for 5 microsecond delay. Then we take the data. So data, for example, I am getting the data to be receiving the data to be some 1101 0100, some 8-bit data I am receiving. So first the MSB bit will come. First the MSB bit will come. So the data I am going to shift by 1, right? So first initially the data is 0, which means it will be 0 0 0 0 0 0 0 0. Now I am going to get this data. So this 1 will come to this position. So what happens to my data? It becomes 0 0 0 0 0 0 0 1, right? So that is what we do here. Then this is OR with SDA. SDA we have set it with 1. So we are going to OR it. So it is 1. Now this will be available in your data. Then we are going to make SCL to be 0. Then when the for loop runs for the second time, what happens? Again I am going to do a shift of data. So now the data is this, right? Now the data is this one, 0 0 0 0 0 0 0 1. Now the second data comes. So what will happen? This bit will go here. So it becomes 0 0 0 0 0 0 1 1. Second bit has come here. Right. Again I am going to do OR with 1. In that case, again what will happen? I will get 1 1 0 0 0 0 0 0. Right. So this is your new data. Again when the third bit comes, 0. When the third bit comes, what happens? This will be shifted. So it becomes 0 0 0 0 0 1 1 0. So now the new bit is 0. Again I am going to do OR with this 1. So like this the process is going to keep on continue until I receive all the 8 bits. Once I receive all the 8 bits, I am going to check the acknowledgement, right? If it is not the last byte, my acknowledgement will be 0. If my acknowledgement is 0, we will put SDA to be 0. If it is a last byte, in that case my acknowledgement will be 1, right? In that case I will get a value of 1 as a SDA. So for all the other bytes except the last byte, my acknowledgement will be 0. For the last byte, it will be negative acknowledgement, right? So it will be 1. Then finally we return the data from this module. After receiving all the 8 bits, then we try to send that value back. So that is how we read the data using your I2C module. Next option is we have to convert our BCD value to a decimal value. So we take a BCD value, for example in seconds, 00H. In this location, let us have 39, right? So 39 seconds. Okay, this is the value available in the memory, in RAM memory, right? In that case, what we need to do, this 3 is stored in a BCD format, same way 9 is stored in a BCD format. So this is BCD values, 9 in BCD format and same way 3 is in BCD format. So this data in BCD format should be converted into a decimal value. So how to do that? We take this BCD value, so 39, shift right by 4 times. Shift right by 4 times in the sense this will go to this location and this will move out, right? 4 times I am going to shift. So 39 means in the sense how it will be there, 0011 1001. Okay, so this is 3, this is 9. Right? So 4 times I am going to shift means this will come here, right? So automatically what will happen? It will be 00000011. Then this data I am going to multiply it with 10. So this is 3, multiply it with 10, so it becomes 30. So this 30 is added with, what is this BCD? BCD is 39, right? So we are going to put AND of 0F, right? So when I do AND operation, this will become 0, this will become 9. So this 9 I am going to add it here. Thereby I get 39. Now this 39 is a decimal value. Earlier it was a BCD value. Now from BCD we have converted into a decimal value. So that is what it is done in this BCD to decimal conversion. Now let us write a program to read the RTC data. Okay, so to read the RTC data, first what we are going to do, we are going to take some variables for storing second, minute and hour information. Then I call the start module where our SCL will be set with 1 and SDA will have a transition from high to low pulse. This will be carried out. Then I am going to send the address of 1307, right? So we have already said address of DS1307 is 11010000, and since we are going to write that address, I am going to put 0 here. Okay, so thereby it becomes D0. So this address we are going to write, and we are going to set the pointer to 00. Right, first location in our RAM memory. So first location in our RAM memory is 00. So we are writing this. Then again I am starting. Now I am trying to read the data. Right. So read the data again 11010001. So now this bit is for read information. Right. So from this location the first data will be read and it will be moved to your seconds. Then second data from 01 location it will go to your minute. Then third 02 hour information will go to your hour variable. So in the first 2 bytes we put the acknowledgement to be 1. The first 2 bytes we put the acknowledgement to be 1, whereas in the last case the acknowledgement to be 0. If the acknowledgement is 1, what happens here? When we go here inside, when the acknowledgement is 1, so this is a read function, right? when this acknowledgement is 1, then SDA will be set with 0. Right? So if it is not the end of the byte, then SDA will be set with 0. If this acknowledgement bit is 0, in that case what will happen? 1 will be sent with the SDA. So thereby it's a negative acknowledgement. So after receiving all this data in second, minute and hour variable, we send the stop condition. So in stop condition what we do? We put SCL to be high, and SDA what happens? SDA should be a low to high pulse. Then after reading the second, minute and hour, this is in BCD format. We have to convert that one into decimal for second, minute and hour. Then after clearing it, we set the time. Then we take, for example, if my time is something like 12, 30, 35 seconds. Okay. In that case, I take this hour 12, right? So I divide it by 10. When I divide it by 10, what happens? I will get 1 as a quotient. So that 1, I need to convert it into ASCII value, and then I have to send it to the LCD. So we make a division here by 10, then add it with the ASCII value of 0, so that I get the ASCII value of 1. Right? Then we send that 1 to the LCD. Then to get the second 2, I have to get 2. In order to get 2, what we do? Again we take 12. Now we do mod of 10. When I do mod of 10, we will get the remainder value 2. So again this 2 is converted into ASCII value by adding it with 0 and sending it to the LCD. Now 2 will be displayed. Then we put a colon. Same thing we try to do it for minutes also. So minutes 30. 30 in the sense, first I will take this 3, convert it into ASCII, put it here. Then take 0, convert it into ASCII, put it in the LCD. Same thing we are going to do it for seconds also. So again after colon, we will take 3, convert it into ASCII and put it here. Then 5, convert it into ASCII and put it here in the LCD. So that is how the data is being displayed on your LCD. So in a main program, what we do here, we are going to make use of all these functions. First we initialize the LCD module. Then I am going to print in the first row, first position of the LCD, we put a real-time clock, retain the output for 2 seconds, then clear it. Then I am going to read the RTC value. When I read the RTC value, it will go to this function. It will go to this function. Then it will start executing this function. First we are reading from the DS1307 IC, convert that values into a decimal value, then try to put the data into your LCD. So that is how the data is fetched from your DS1307 IC and it is being displayed onto your LCD. Now let us look at the programming and circuit part. So the programming is done using your micro C Pro for AT51. So the same code is given here: LCD connections, I2C connections, delay function, start condition, stop condition, I2C write, I2C read, BCD to decimal conversion, read the RTC module, and then finally your main function. Once you have written the code, build the code so that it gets converted into a hexadecimal value. Now let us build the circuit using Proteus. In Proteus, we have built the circuit where I have a AT89C51 microcontroller. It is connected with the oscillator circuit with a frequency of 11.0592 MHz. Then there is a reset circuit. Then we connected DS1307 IC to your port 2.0 and 2.1 where we are going to generate a software based I2C connection. And we support this IC with the help of a 32.768 kHz. And in port 3, we try to connect your LCD module. Now we will try to dump that hexadecimal file, go to edit properties, select the hexadecimal file, import it to the IC. Select the oscillator frequency, press OK. Now we have to check our output. To check the output, run the simulation module. So you can see real-time clock. Then you can see the time gets displayed. So our minute and second information gets updated here. So like this we can create our own real-time clock using AT89C51 microcontroller. So in this tutorial I discussed about how to design a real-time clock with the help of a LCD and a microcontroller. Thanks for watching. Please subscribe for more technical learning. The complete code and simulation of the project is available in the GitHub repository link given below. Thank you.